So I have 77 divided by V0 sine 12 is equal to, oh no, this is a typo. Sorry, typo. This is equal to V0 sine 12 all divided by 5. So you want to solve for V0, you got to get it by itself. I'm going to multiply here and multiply here, so I have 77 times 5 is equal to V0 squared sine 12 cosine 12. So this is a calculator value, so I put this in, take this, divide by these, take the square root, and I end up with V0 is equal to, survey says, 43.5 meters per second. So the problem is cool because it asks you for the V0. A lot of times you're given the V0 and then asks for the other stuff. But the structure remains the same, where you have your vertical information, your horizontal information, treat them independently, and then link them through the time. That's the thing that's important, is that the only thing that these two columns share is the time, and that's how you can link them. Okay, that's great. We're at problem 27. Problem 27. Okay. Problem 27, another picture. Okay. So it has a bomb or a missile of some sort, and it's going like this, and it's gonna hit the ground here. It's got a jet somewhere. So here's the plane. So the plane is going at some angle here. Oof. How do I draw this? So the bomb was let go sometime previously. Okay, and it's going to fall into a parabola. And so the plane let it go when the bomb was at some angle, and it falls some sort of distance here, d. Okay. All right, again, you have it in the book. It's not that big of a deal. But it says, a certain airplane has a speed of 290 kilometers per hour and is diving at an angle of 30 degrees below the horizon when the pilot releases a radar decoy. The horizontal distance between the release point and where it lands is 700 meters. Okay. So there's a couple things about this that are hard. So this is okay here. It says that this distance here is 700 meters. One of the problems is it gives you the speed, gives you the V0 here for the plane at 290 kilometers per hour. That's a problem for us because the units that we need to use are meters and seconds. So we need to figure out what is 290 kilometers per hour in meters per second. If you want to talk about how to do that, we can. I'm just going to provide the answer for you because it's a different problem. So it's 80.6 meters per second. I probably put it into Google. We'll see. If you need to know how to convert it, I'm happy to tell you. But, so we have this here. We know that this angle theta is equal to 30 degrees. Now, it's negative 30 because it's 30 degrees below, but we'll see how that manifests in a second. Okay. And so, it asks for how long is the decoy in the air and how high was it released from? So we're going to do the same thing we always do, and we're going to consider the horizontal and vertical parts of this. Once you consider the horizontal and vertical parts, the rest is easy. So let's do the horizontal. We have delta x, Vx, t, of course. Vertical, delta y, v0y, vy, a, and t. So what do we know? We know how far it went horizontally. What's that? That's this, 700 meters. We don't know the Vx, we don't know the T. Okay, stay right there. This is actually what we're solving for. That's good. We don't know this, we don't know this. We know this is negative 10 meters per second, and of course we don't know the time yet. Okay, so let's start with our drawing. It says that the bomb is released at an angle of 30 degrees. So let me draw 30. That's the V0. That's the V0Y. This is the Vx. What's nice about this is I know these two values. I know this angle here is 30 degrees, and I know this is 80.6 meters per second. And so given those, I have the hypotenuse and the angle, and I'm looking for the adjacent side. No problem. Vx is equal to V0 times the cosine of my angle, 80.6 cosine 30. Let me check. 69.8. V0y is equal to V0 times the sine of the angle. 80.6 times the sine of 30. So now I have these two values. I can just put them into my table up here. And now that I know that, I can apply my mathematical equations to these. Delta x is equal to Vxt, 700 is equal to 69.8 times t. T is equal to 10, it's 10, 10.8. I mean, it's probably 10.01 or something like that, was about 10 seconds. Cool. So this is 10. Guess what? That makes this 10 also. So that's the first question. How long does it take for it to get there? It takes a good 10 seconds. And then from how high was it released? Well, start with the same mathematical model we always use for the vertical side. This is what we're solving for. Negative 5 times 10 squared plus 40.3 times 10. Now, there's a typo here. Not really a typo. I made a mistake on purpose because if I look at this here, the V0y is in the down direction. The value is 40.3, but because it's down, this is actually a negative vertical velocity, which means I'm going to just change my sign to minus. Okay, so this is at least negative 500 plus another negative 400. So how about negative 903 meters? And so that means the distance it fell from Boy, I like 29. I don't like how each of these problems takes up the whole board, though. Okay. 29 is hard because it's just words, right? It's just words. A projectile's launch speed is 5 times its maximum, is 5 times its speed at the maximum height. Find the launch angle. That seems weird. So let me draw a little picture here. So here's the ground. If I'm going to launch it, right, it's going to go in a parabola. Okay? So when we go to draw the launch speed here, okay, we know we have 3 vectors. We have the initial horizontal velocity, which is here. We have the initial vertical velocity, which is here. And then the resultant. The resultant is the actual launch speed itself. So if I put these two things together, okay. So this is the launch speed right here. We'll call that V0. So what happens to the projectile as it goes from here to here? Well, what do we know about the horizontal speed? The horizontal speed totally stays the same. So no matter where I were to draw it, even if I were to draw it over here, horizontal speed's the same. Here, horizontal speed's the same, right? The vertical speed changes. Here, back on the ground, it's because of symmetry, it's the same. So this one would be the same length. That would be the same length as that. Here it'd be less because it hasn't sped up as much. Is that cool? But what about at the very top? At the very top, it still has the same horizontal speed. Okay, this is Vx, that's Vx, this is Vx, and this is Vx. But the interesting thing is there's no vertical speed. So here I have a V0, here I have a Vx, and the problem says that, given the construct, it says the launch speed, V0, is equal to 5 times the speed at the top of its path. The speed at the top of its path is only the Vx. So that's how you end up with this statement right here. Let's come over here and look back at this. What do I know about my two terms here? Here's my launch angle theta, which I'm looking for. I know that Vx is equal to the V0 times the cosine of my angle. So here I have 2 variables in one equation. Here I have 2 variables in a second equation. 2 variables, 2 equations. I can solve. Let's plug this into here. V0 is equal to 5 times V0 times the cosine of theta. Divide both sides by V0 and divide by 5. I have 1 over 5 is equal to cosine theta. Theta is equal to the inverse cosine. It's like 60 something, right? 78.5 degrees. So the problem with this problem was that conceptually it's a little bit challenging in terms of the fact that you have to be able to visualize the picture, know there's a relationship between V0 and Vx, and know at the top of its path it still is moving in the horizontal direction, but no vertical direction. So the speed is Vx. Oh, this is fine. The next one is 33. But 33 is almost the exact same problem as the other one we did with the plane. But this time you're just given different things. So it says, a plane diving with a constant speed and angle of 53 degrees with the vertical. Okay. So this one's hard because it gives you an angle of 53 degrees with the vertical. So here's the vertical. Okay? And your plane is diving 53 degrees with the vertical. So this is 0, so 53 degrees would be like this. Okay? Now, what that means is that this angle here is 37 degrees. Now, you'll see 37 and 53 all the time woven into physics textbooks and math textbooks for that matter, because 57 degrees, or 53 degrees and 37 degrees denote a 3, 4, 5 triangle, which is a very cool thing. So it's always going to be some integer multiple of 3, 4, 5. All right, so this is what we have here, and then it says that the projectile is released. Okay, so let's say the projectile is released here. So its velocity is down and to the right. Okay? And that means the horizontal velocity would be here. The vertical velocity would be here. So this is my V0y. This is my Vx. And what would actually happen to it was it wouldn't continue along this path, it would fall like that. Okay, I like it. I like it a lot. The vertical release projectile at an altitude of 730, and it hits the ground 5 seconds later. Okay. So what about the horizontal? And the vertical? So we know the time, 5 seconds. We know this was negative 730 meters. This is negative 10 meters per second per second. Excuse me. And again, we know something that's interesting here is the angle that's given is not the angle that we're going to use, because I want the angle that it makes with the horizontal. So we're going to use the 37 instead. So we're going to call the 37 my angle theta. We're going to put it in right here. So that means that Vx is equal to V0 times the cosine of 37. And the V0y is equal to the V0 times the sine of 37. It asks for, what is the speed of the plane? No problem. I'm going to take this, substitute in here, V0 sine 37. And if I look at my parent equation, 1/2 gt squared plus V0yt. This is negative 730. This is negative 5 times 5 squared plus V0 sine 37 times 5. And this is one equation with one variable. So I solve for it, and V0 is equal to 201 meters per second. So coming over here, I know this is 5 seconds because it was given. If I want to get my Vx, I can plug and chug that bad boy. 201 times 201 times the cosine of 37 So b in the x direction is equal to, oh, actually I resolved for it, that's fine. 160.5. And so now if I want to know how far, (605 meters). That's how far it goes horizontally before it hits the ground. Okay, I gotta check the time. So we're going to do 45 now. And 45 is by far the hardest problem that we'll encounter, because there's a conceptual issue with it in terms of the question itself. It says, does this thing happen? So we got to figure out a way to figure out whether it happens or not. So let me draw this for you. Okay. So it gives us a kind of a ramp scenario here. I'll draw it in black. So it says, like, you have a ball here, and then there's a ramp here, and then there's a plateau. And it says that this distance here, I think it's called D1, and then this distance here is called D2. So this looks like this. So those are D1 and D2, and those are given to us, which I like. 45. 6 meters and 3.6 meters. So this one here is 6 meters, and this one here is 3.6 meters. So those are D1 and D2. Those are going to be important later. Ooh, did I write that right? Yeah, D1 and D2. Okay, those are going to be important later. Okay. It also gives you something else. It tells you that it's launched at 10 meters per second at an angle of 50 degrees. Okay? 10 meters per second at an angle of 50 degrees. So here's the ball it's launched. It's 50 degrees, so it's pretty steep. Okay, so this is 10 meters per second, and this whole angle here is 50 degrees. All right? So if I start with the thing that we always start with, and that's the horizontal and vertical components. So here's the horizontal component. Because it's an angle of